Uncertainty in deep learning is not a theoretical luxury. In production AI systems, uncertainty directly influences safety, compliance, and financial risk. When a medical diagnostic model makes an overconfident, incorrect prediction, or when an autonomous system acts on unreliable output, the consequences extend beyond accuracy metrics. Real-world AI teams must quantify and manage uncertainty as a core system property. Traditional neural networks produce deterministic point estimates. Bayesian approaches instead model posterior distributions over parameters, enabling predictive distributions that capture confidence and variability. This shift from fixed weights to probabilistic reasoning changes how systems are evaluated, deployed, and monitored. Most early AI professionals misunderstand uncertainty by equating softmax probabilities with calibrated confidence. In practice, deep networks are frequently overconfident and poorly calibrated. Engineers who understand epistemic and aleatoric uncertainty, variational inference, and ensemble approximations are better positioned for roles involving high-stakes AI deployment. Mastery of uncertainty quantification signals architectural maturity and distinguishes production-ready engineers from benchmark-focused model builders. This session builds a structured understanding of uncertainty quantification in modern AI systems. We examine Bayesian neural networks, posterior distributions, and scalable approximation methods such as variational inference and ensemble modeling. The goal is not only conceptual clarity, but operational readiness for production environments. In real-world AI teams, uncertainty informs decision thresholds, fallback mechanisms, and human-in-the-loop workflows. Engineers are expected to justify model confidence beyond raw accuracy. Hiring managers increasingly evaluate whether candidates can reason about risk and reliability rather than simply optimize metrics. A common career limitation is focusing exclusively on predictive performance while ignoring calibration and uncertainty estimation. Professionals who develop competency in uncertainty modeling are trusted with safety-critical systems and move towards senior architectural roles within AI organizations. Uncertainty in machine learning is commonly decomposed into epistemic and aleatoric components. Epistemic uncertainty reflects uncertainty in the model parameters due to limited knowledge or insufficient data. Aleatoric uncertainty captures inherent noise in the data generation process that cannot be reduced through additional training. In production AI systems, this distinction affects strategic decisions. Epistemic uncertainty can often be reduced by collecting more diverse training data, while aleatoric uncertainty requires robust modeling and risk-aware decision policies. Engineers must interpret predictive variance carefully to determine whether model improvement or process redesign is required. Most early professionals assume all uncertainty diminishes with more data. In reality, only epistemic uncertainty behaves this way. Failing to distinguish between the two leads to misguided investment in data acquisition or infrastructure.
Professionals who internalize this decomposition provide more strategic guidance within AI teams.
Bayesian neural networks replace deterministic weight estimates with probability distributions, allowing the model to express uncertainty over parameters. Instead of learning a single optimal weight configuration, the objective is to infer a posterior distribution conditioned on observed data. Predictions are then generated by marginalizing over this posterior, producing distributions rather than point estimates. In real-world AI teams, Bayesian neural networks are considered when uncertainty estimation is mission-critical, such as in medical risk scoring or safety monitoring. However, exact Bayesian inference is computationally intractable for large-scale networks, requiring approximation strategies. Engineers must balance theoretical rigor with infrastructure constraints. A common misconception among early practitioners is that Bayesian methods are impractical for modern deep learning.
While exact inference is expensive, approximate Bayesian approaches are viable and increasingly relevant. Professionals who understand both probabilistic foundations and computational trade-offs are better positioned for roles in high-stakes AI systems where reliability outweighs raw throughput.
Variational inference provides a scalable approach to approximating intractable posterior distributions. Instead of computing the true posterior directly, a parameterized distribution is optimized to minimize divergence from the true posterior. This is typically achieved by maximizing the evidence lower bound, commonly referred to as the ELBO. In production AI systems, variational inference enables Bayesian reasoning at scale, especially in large neural networks where exact inference is impossible. The reparameterization trick allows gradients to flow through stochastic nodes, enabling efficient optimization using standard backpropagation techniques. Many early AI professionals treat ELBO optimization as abstract mathematics disconnected from practice. In reality, the balance between reconstruction fidelity and regularization directly affects model reliability and uncertainty calibration.
Engineers who understand this balance can design probabilistic systems that remain stable under distribution shift and evolving data conditions.
Variational autoencoders combine a reconstruction objective with a KL divergence regularization term that aligns the approximate posterior with a chosen prior. The reconstruction term ensures meaningful latent encoding, while the KL component controls model complexity and uncertainty calibration. In applied AI teams, VAEs are used for anomaly detection, generative modeling, and representation learning. Understanding the interaction between the reconstruction loss and the KL penalty is critical for stable training and meaningful latent representations. A common mistake among practitioners is focusing exclusively on reconstruction accuracy while neglecting the KL component. This often leads to posterior collapse or poorly structured latent spaces. Professionals who carefully monitor the ELBO components demonstrate disciplined modeling practices and are better prepared to design generative systems suitable for enterprise deployment. Monte Carlo dropout interprets dropout regularization as an approximate Bayesian inference method. By performing multiple stochastic forward passes with dropout enabled at inference time, the model produces a distribution of predictions from which predictive variance can be estimated. In production environments, MC dropout provides a practical mechanism for uncertainty estimation without fundamentally altering model architecture. It is computationally lighter than full Bayesian training and integrates seamlessly into existing pipelines. A frequent oversight is treating dropout solely as a regularization technique. Engineers who leverage it for uncertainty quantification gain additional insight into prediction reliability with minimal infrastructure changes. This practical understanding differentiates applied AI practitioners from those who rely exclusively on theoretical Bayesian frameworks without considering operational feasibility. Ensemble methods estimate uncertainty by training multiple independently initialized models and aggregating their predictions. Variation among ensemble members provides a practical signal of epistemic uncertainty. Deep ensembles are often considered a strong baseline for reliable uncertainty estimation. In production AI systems, ensembles are widely used because they are straightforward to implement and empirically robust. Independent training reduces correlated errors and improves predictive stability under distribution shift. Engineers must consider computational cost and inference latency when deploying ensembles at scale. A common misconception is assuming ensembles are inefficient compared to Bayesian neural networks. In practice, ensembles often outperform more complex approximations while remaining operationally manageable.
Professionals who understand this trade-off are better equipped to design uncertainty-aware systems that balance reliability and performance within realistic infrastructure constraints.
Calibration ensures that predicted probabilities align with observed outcome frequencies. A well-calibrated model assigning 80% confidence should be correct approximately 80% of the time. Techniques such as temperature scaling adjust logits post-training to improve probability alignment without retraining the entire model. In real-world AI teams, calibration affects user trust, regulatory approval, and automated decision thresholds. Expected calibration error provides a quantitative metric for evaluating misalignment between confidence and accuracy. Many early practitioners assume high accuracy implies reliable confidence estimates. In reality, modern deep networks are often overconfident. Engineers who incorporate calibration assessment into evaluation pipelines reduce deployment risk and strengthen stakeholder confidence, demonstrating professional maturity beyond raw metric optimization. Predictive uncertainty is commonly expressed through mean and variance estimates. Aleatoric uncertainty is often modeled directly in output distributions, while epistemic uncertainty is estimated through ensembles or Bayesian approximations. Together, they form a more complete picture of predictive reliability. In production environments such as finance and healthcare, predictive variance informs risk aware decisions. Systems may defer action, request human review, or adjust thresholds when uncertainty exceeds predefined limits. Engineers must integrate uncertainty outputs into downstream decision logic. A frequent oversight is ignoring variance and focusing solely on point predictions. This behavior leads to brittle systems that fail silently under uncertainty. Professionals who operationalize predictive variance into monitoring and control mechanisms design more trustworthy and resilient AI solutions. Active learning leverages uncertainty estimates to select informative samples for labeling. Uncertainty sampling prioritizes examples where predictive confidence is low, improving data efficiency and accelerating performance gains. In enterprise AI teams, active learning reduces annotation costs and focuses human effort where it provides the highest value. Acquisition strategies must balance exploration and exploitation to prevent biased dataset construction. A common professional mistake is relying on random sampling during dataset expansion. Engineers who implement structured, uncertainty driven acquisition strategies demonstrate resource awareness and improve long term system robustness, positioning themselves as strategic contributors rather than reactive problem solvers. In reinforcement learning, uncertainty guides exploration strategies. Posterior sampling and optimism based methods encourage agents to explore uncertain regions of the state space while balancing reward optimization. Modeling uncertainty improves sample efficiency and reduces catastrophic exploration failures. In production control systems and robotics, uncertainty aware reinforcement learning enhances safety and reliability. Engineers must design exploration mechanisms that consider operational constraints and risk tolerance. Many early practitioners focus exclusively on reward maximization without modeling uncertainty. This approach can lead to unstable policies in real world environments. Professionals who incorporate probabilistic reasoning into reinforcement learning design demonstrate advanced system level competence suitable for high responsibility AI roles. Robust decision making integrates predictive uncertainty into action selection. Systems may defer decisions, request human validation, or apply conservative thresholds when uncertainty exceeds acceptable limits. This reduces risk in high impact environments. In production AI systems, especially in regulated industries, uncertainty aware decision policies are essential for compliance and safety. Engineers must collaborate with product and risk teams to define acceptable confidence thresholds. A common mistake is deploying models without integrating uncertainty into decision logic. Professionals who align model outputs with business risk frameworks build trust and demonstrate cross functional leadership, which significantly influences career progression in AI organizations. Evaluating uncertainty requires quantitative metrics beyond accuracy. Expected calibration error measures the gap between predicted confidence and observed outcomes. Sharpness reflects concentration of predictive distributions, while reliability assesses correctness. In enterprise AI teams, out of distribution testing and stress testing validate model behavior under domain shift. Engineers must design evaluation frameworks that simulate realistic edge cases before deployment. A frequent professional limitation is ignoring uncertainty validation until failure occurs. Practitioners who proactively measure and monitor uncertainty build resilient systems and establish themselves as dependable technical leaders within AI organizations. Uncertainty quantification transforms deep learning from pure prediction engines into reliable decision systems. Bayesian neural networks, variational inference, ensemble strategies, and calibration techniques each provide complementary mechanisms for modeling predictive uncertainty. In production AI environments, reliability and risk awareness are as important as accuracy. Engineers who integrate epistemic and aleatoric reasoning into system design influence deployment policy, regulatory compliance, and stakeholder trust. Many early AI professionals focus narrowly on model performance benchmarks. Long term career advancement requires understanding how uncertainty interacts with business risk, operational safeguards, and human oversight. Mastery of these principles signals readiness for senior architectural roles and positions practitioners to lead responsible AI initiatives.